All right, what did we do last time? We started talking about LR parsing. I guess we can start with some announcements though. So everything due on Friday, we have both projects. One of them is due, one of them is extra credit. Then the assignment, I know that's a lot. And then we have our last exam. There was a slight amount of cumulative content that I wanted to be able to ask about. That's not bringing back material from past exams. It's more so looking at the course as a whole, languages as a whole, based on everything that we have studied. So go ahead and take a look at the study guide, all of that, and the kinds of questions that I would ask about how everything ties together is all on the study guide. I plan to do that full review on Friday. So if you can come prepared with questions, that would be great. Otherwise, I will do my best to come up with some additional practice problems, struggle points that I've seen. And we will go from there. We prepare for a final exam, even though it isn't a final exam next week. All right, we did start talking about the concept of LR parsing. The reason we care about LR parsing, and it is more complicated than LL parsing, is that more grammars are LR than LL. So we would prefer, given that a language is LL, to use that LL process. But if it is not LL for some constant K, then we can at least try LR parsing, and it's quite possible that the grammar is LR. So it is worth knowing. Make that go away. Yes. We were in the process of looking at how an NPDA would be constructed from a context-free grammar following this process. Right? Did we go through all of this? I think we might have. Yes, I think so. So we ended up, yeah, we certainly looked at this. All right, so how do we use the NPDA? So we are going to be shifting symbols from the string onto the stack as we find ways to, as we've yet to find ways to condense them into non-terminals. As we do this, we're going to be popping off the right-hand side, replacing with the left-hand side. We call this a reduction. And what's nice about non-determinism is that we can do these in parallel. We don't have to choose whether to shift or reduce. Given that both are something that you can do, since it is a non-deterministic pushdown automata, we can just do both. If there exists a path to a final state via a shift or a reduce here, we will find it. Granted, since this is not a realistic machine, since we don't have non-determinism, we would obviously have to search in real life. But the goal of the LR parsing will be to make sure that we don't have to choose. So we need this additional information to turn this non-deterministic process into a deterministic one, because what we want is a linear time deterministic algorithm for determining the membership problem. And so far, we have a linear time non-deterministic algorithm, which we obviously can't write. So what other information do we need? With LL, we stored the look ahead to figure out, okay, how long of a look ahead do we need to be able to remove this ambiguity? So we built the LL1 table, looked for conflicts, built an LL2 table, looked for conflicts, built an LL3 table, or we looked at the problem and saw if we could calculate that K value. If we could use a look ahead of 5 characters to be able to solve the problem, as was in one of the examples in the last slide deck, then we had an LL5 table that we needed to create to be able to parse this in linear time. So we ended on this note, I think, on this LR parse. So same grammar as before, string is ABCAB. We wanted to trace this with a look ahead of 1 symbol. we will find that there are multiple options here. We could shift and we could reduce at a couple of points. So let's take a look at it. So there is no guesswork with the full LR algorithm, but let's go ahead and take a look at what's actually happening here. So we have a choice between a shift and a reduce. A shift just adds the current symbol in the string into the top of the stack string. And the reduce takes the top of stack string and replaces it with a left-hand side. If there is a production, some non-terminal arrow what we have on the top of the stack. So what do? We start with the bottom of stack symbol, which we just have right here. We're in state Q0, and we know that all the work happens in Q0. So we have to choose whether we are going to shift or reduce from here. There is nothing with a lambda. So we don't have the ability to reduce yet. There's nothing we can do that it's going to create a non-terminal out of nothing. So we have to shift. We're going to shift and put the A from the string onto the stack. Great. So that was the first symbol from the string here. Now it's on the stack. The question is A right-hand side to any production? And the answer here is no. We don't have something arrow A. So we cannot do a reduce again, we have to do a shift. Which means we're going to move past the A to the B, we're going to put the B on the stack, and now we have B A or A B in that order. The question is now, can we, given where we are in the string, can we reduce anything? And no, we still cannot. There's nothing with AB anywhere on the right-hand side. So now the question is, what do? We bring in the next character from the string. Now we have ABC. And now we have an option here. We could shift, we could reduce, we could bring down the next A, but ABC turns out to, there's a C that is the right-hand side of a production, A arrow C. So we have the option to bring down the A, or we could do a reduce, take this C, turn it into an A. So since this is non-determinism, we can do both at the same time. We can start to explore both of those state spaces. The one that is presented here is the one that leads us to acceptance. So there's something about this string that says we should probably reduce here. But you can see that with none of this other work done, that is an obfuscated problem. Is that something that we actually want to do? We don't know until we really see it through to completion, see whether it accepts or rejects from there. So we've done the reduction, we've turned this C into its left-hand side. So now we have the terminals AB and the non-terminal A on the stack. And we see that from here, we're going to shift the A. But as soon as we have that shift, there's now another grouping here that makes sense. We have B capital A, which is the right-hand side of a production. So we have the opportunity to reduce if we want to. We can turn B capital A into A. So that's what we're going to do. A is also the right-hand side of a production. You have S arrow A. So we can reduce this A into an S. There's no right-hand side that's A capital S, but we're also not done with the string yet. So we can shift the last B down onto this. We see A capital SB, which is the right-hand side of a production, which means we can reduce. Once we reduce, we can always go ahead and move from Q0 to Q1. When we do this, it gets rid of the start non-terminal. So there's a transition from Q0 to Q1. So you can see that we got rid of the S and moved to Q1. When that's the case, we can also transition from Q1 to Q2, which checks for this bottom of stack symbol. If that's the case, then we can accept. So this is LR. However, it's not the full algorithm. What cheat did we do here in order to make this all work? There's something that we did here that is not allowed. How did we determine that we could do this reduce?
Given what's in the stack, the A, B, the A.
Right. However, how did we know this was on the stack? We're looking beyond just what's on the top of the stack. We're digging into the stack to say, is there a right-hand side? So we need the knowledge of what is stored on the stack, and that is what we have not covered. How do we know what's relevant underneath where we are? How do we store where we are in each one of these right-hand sides based on the characters that we are shifting? We need to store that information so that we know without having to dig that we are in this situation. When we put this B there, there's something that we could say, we've seen this B now. However, when we do this C, we can't get rid of that information because this may eventually reduce and become something that we can go, oh, this is the next character we were looking for in this. Without having to dig back beneath it to see that that B is still there. How could we store that information? So that we would know when we had a full right-hand side. That's the fun of the LRL algorithm. And I use fun very liberally here. But if we could find that information, then we could implement this process. So let's give these some names. We're gonna define two terms here called an item and a closure. So to be able to do this, we need to know when a right-hand side is on top of the stack. That involves us digging down below that top symbol. Since we know each of those symbols is put on the stack one at a time, we can work with that. We can start to store relevant information. So now we're going to do this concept of adding a marker to the right-hand side of all productions. And this marker is going to tell us what of relevance is on the stack. So that when we make an operation, we can go through and change those markers. So that we know what we can do with what's on the stack. So an item is probably better called a marked production. So there's just going to be the right-hand side and there's going to be a dot. And that dot tells us how much of relevance of that right-hand side is currently on top of the stack. So items to the left of this dot are on the stack in order. Items to the right of it are not. So you can note from that rule that that dot can appear anywhere in the string itself. If it's at the very beginning, that just means we haven't seen anything yet that would help us to be able to reduce this particular right-hand side. If it appears on the very right, that tells us everything is on the stack that we need to be able to reduce this right-hand side to its equivalent left-hand side. Questions on this concept? So that is an item, a right-hand side of a production with a dot in it somewhere. So how many possible places are there for that dot? If there are n symbols in the right-hand side, there's n+1 possible positions. It can basically be before the first position that we will call position 0. It could be after the last position, which we will call position n. The trick comes in recognizing when we can do reductions that become the ability to move the dot forward. Or giving up on where the dot is and trying to move it back to the beginning. So how is that logic done? So It's especially challenging when the next symbol is a non-terminal in an item. To be able to move it past, we need to move it past a non-terminal. So how do we know that what's coming is building up to a reduction to that non-terminal so we could move past it? Does that make sense?
The question makes sense. Don't know how to go about knowing how to.
Yeah, so we have some right-hand side, like S arrow A capital S B. So if we were right here, saying the A is on the stack, and we need to see something that can become an S. And what happens if what's on top of the stack now becomes another A? Is that the beginning of something that can be done, reduced into this capital S? We don't know, it depends on the rest of the grammar. But that's the idea is when we want to move this forward or leave this where it is, saying what's on top of the stack could become an S. Or if, for instance, maybe this is our S, so on our stack, we have an A, and the next character we see is a B. Since there is no B that begins an S arrow, nothing that starts with a B, now we know that we can't possibly reduce this down into an S. So now we can move this dot back to here. But if we saw an A, now that A can be reduced to an S, which could become the S that we need here. So if we see an A, then we want to keep the dot here. Because now there's a way to move past that S. So that becomes the challenge of recognition. All right. So closure is an operation. It's a method, it's a function, whatever you want to call it. So we have a context-free grammar. That closure says we're going to initialize the set. So it's just a set. It's going to contain a single element. A arrow W dot V. And that's the closure of W dot V. So it's going to contain that element. We're in a loop until no more items are added to the set. For each production in the set, if a dot appears before a non-terminal, we will add a new production to the set, B arrow dot, the right-hand side for every possible right-hand side. Let's give you an example. So a closure question looks something like this. We have a context-free grammar, and you can calculate the closure of something. Here we care about the closure of S arrow A dot SB. That says what are all of the items that we want or that we could use to continue this process. So we know that a closure contains itself. So the closure of that starts out as a set with a single element that is itself. The next question we ask is the marker to the left of a non-terminal? So we need both S productions with the marker to the left of their right-hand sides. That's going to become, those are going to become elements of this closure. So now we have three elements to the closure. We have itself, and we have every element of S at the beginning. S arrow dot every possible right-hand side for S. So now the question we have to ask is, do any of these elements contain items where the dot is to the left-hand side of a non-terminal? And the answer is yes, the last one. Because we have S arrow, something that starts with a non-terminal, we end up with S arrow dot A. So now we need to expand this and find what are all of the possibilities that A could become of the next terminal that we could be looking for in our string. So we now add every A production with, again, the dot on the left of all of those productions. So we get a couple more elements. Now we loop this process again. Do any of these productions that we haven't already handled start with a dot before a non-terminal? Itself, we already handled that. Already handled that, already handled that. This is a dot before a terminal, this is a dot before a terminal. So nothing new that is a dot before a non-terminal. So this procedure terminates. So we didn't add any new elements left of a new non-terminal that we haven't already done. Even if we get a new production that is something .a, since we've already expanded that, we know we've already added those, and since this is a set, there's at most one copy of everything in that set, so we wouldn't be adding anything new anyway. We can shorthand that by saying it needs to be a new non-terminal that hasn't been expanded before in this process. Questions on this? How do we feel about the concept of iterating a grammar and adding to a closure? Right. So how does this help us? If we have a marker, this dot, to the left of S in an item, this means that it tells us the A is on the stack, and we're looking for this capital SB to not be on the stack. But we need to know whether we are in the process of starting something that could lead us to this S. So let's say a shift operation places an A on the stack. We know to get that S on the stack, we have to reduce something into that S, which means we're looking for some right-hand side of an S. And eventually, everything is going to be on the stack for some element of its closure. So as long as we're seeing something as a shift that is an element of some element of its closure, then we can move that production forward, saying we've seen what we need for that, basically. So once we see that something that reduces to S is on the stack, we can find that item, we can reduce it, and then we can move the dot past the S, saying that now that S is on top of the stack. Did that make sense? I don't know if that makes sense. We basically just need to find all the elements of some right-hand side S arrow something. But the closure helps us with this because if we look back at all of the elements in that closure, we can see all of the elements that we would be seeing that would help to start that closure process. So if we can now iterate through this closure and say the next element we see is a B. Can that B possibly help us to move forward from here? And the answer is yes, because of this. Because this element is in that closure, if we see B capital AC, then that reduces to an A, which can reduce to an S, which can reduce to the S that becomes the thing that we move past it. So that since this element is in there, that tells us the next shift. Does that move us toward being able to do this, yes or no? Yes. Yeah. So moving past everything else. Here is, the idea is we're actually going to be producing a DFA. Yes, these come back too. So the LR parsing stack, everything that we need for this ends up being a DFA, and we're going to construct that DFA by computing closures. Basically, what happens when we see a particular symbol, we do a shift. How does that help given whatever state that we are in? So the state is going to be one of these items. By calculating the closure of that, that will help us to determine what transitions we can make whenever we see shifts. Can we do a reduce from there? So we're going to iteratively calculate this DFA that represents what it is like to be in any one of these states, seeing any one of these next symbols. Does it help us get ready to reduce? So we're going to complete this parsing, assuming that we can look multiple positions down the stack. But we'll end up not needing to after we build the DFA. So we're going to be constructing the DFA, assuming that we can look down the stack. And then the result of this will be a DFA where we don't need to do that. It's giving us a DFA that represents all possible states that we could be in terms of an item. And then via any operation that we could take, any symbol that we could see, any reduction that we could do right from there, what are the next options for us? All right, every state in the DFA is going to have a set of items from the grammar to indicate which symbols are on the stack and which have yet to be added. When we parse a string, we trace through that DFA, and the final state indicates that we have a right-hand side on top of the stack and we're ready to reduce. So let's actually construct one of these, because I think this is a lot to take in. We'll come back to this algorithm. So our old friend, the same grammar. How do we build the DFA that models this process? So we're going to add a new start symbol and a production S prime arrow S that just tells us that we can start, basically. It seems like a waste, but there's a point to it. We are going to number all of the productions in the grammar. So we end up with a list that looks like this. Element 0 is this new production that we have made, and every other production is just each of the individual productions in the grammar, stripped of ors. Then we start in on the DFA. Excuse me. With state 0, we now need to calculate the closure of this S prime arrow S. And that's going to give us kind of the closure of the very beginning state. You can see that this means that we put a dot ahead of this S, which says, what do we do to move past this S? So now we need to figure out, all right, let's add both S arrow productions to this closure, which produces the A, which means that we have to add every production A arrow something to the closure. And now you can see that if we see an A or a B or a C, we are building toward this, at least one string in this language. Right, let's say this alphabet contained a D as well, so it's not anywhere in the grammar. You can see that from this closure that no string in this language starts with a D. So this set is going to be associated with state 0. So every item in this closure is now a list that is attached or is part of the object that is the state Q0. So you can imagine coding this. You would have a class representing a state, and one of your fields would be a list of some kind of strings where you have the marker followed by something. And every one of those is an item in its closure. Excellent. Now, we need to figure out which state to expand. Since there's only one state, we're going to expand it. Each of the elements associated with it, so every element of this list is going to create a new transition out of this state. Basically, what happens if we see a first element to this? So if we see an A as the next shift, then we can say something about a transition that's out of this state for when we see that A. So for the first one, we're going to move the marker over the S. That says if we can reduce, basically, if we end up with a transition back to here with the S on top of the stack. So we can transition on seeing an S on top of the stack. We could move past this to a position where we could say this is now in this language. Right? We do a reduce all the way down to S. If S is on the stack, we get rid of the S, and if it's the bottom of the stack, we accept. But we can now move past this S if we can prove somehow that this S is on top of the stack. So by looking at that, we can determine that that creates a transition out of the state. So the closure of this doesn't do anything. It doesn't add anything new to that. So we're going to make a new state one and associate this item with the now marker past the S with that state. So we now have a Q1 with just this one item associated with it. For the next item, a transition out of this would read an A, move the marker to here, and then add everything in this closure, since this dot now comes before a non-terminal. We need to figure out what all of those items are. Luckily, it's going to be exactly the same subset. And we're going to associate that with a new state that says from here, when we read an A, we're in this state, where transitions out of that would look like everywhere that would start something that could start to move us past this S. So that gives us yet a new state. Closure adds a bunch of new items. We now have a state Q2, and we'll associate this set of items with that state. And you will continue this for states 3, 4, and 5 as options out of Q0. So when we get to that point, we have something that looks like this. And this defines the transitions that are possible out of Q0. So take a minute, take a look at this and let me know if you have any questions about it. Do we see how we get all of this?
Before, digging to dot C.
So this is saying that to go, sorry, Q4, it's the B. So this is associated with that production. This is saying we saw that B. So the equivalent of, we can now move the dot over here when we do that. And that becomes the first element that we see here. That says we are, if we can get to this point, we could then reduce and go back to Q0. So this is not a complete DFA. This is just the first pass of everything out of Q0. And then we want to say, all right, well, if we move the dot to here, we now need to kind of expand this A and say we could eventually get back to Q4 if we could resolve what's on this A. And any of those options start with anything A arrow that we see here. So for instance, if we were to see a C next, there'd be some transition out of Q4 consuming that C, some transition back to Q4 that would reduce that into the A, such that we could make a transition back here that would allow us to say, hey, we actually consumed this A. So we can now move past this A here. It gets quite complicated, but yeah, that's the logic of how we how we got to that point. Does that help? Does that make sense?
Yes, that helps a lot, thank you.
So now we just have to pick a new state, and we're going to find all transitions out of that state. And then pick another one and find all transitions out of that state, and eventually this process terminates. Because it's a DFA, since it's a finite production grammar, you can only have so many possible states, although it can be a lot. This is not something that's easy to find a problem to do by hand, because this ends up being a very large DFA. But let's continue for now and find some additional states. So we now need a queue to store the states that we want to expand. So states 1, 3, and 5 back here only have a single element with the dot on the right-hand side. If that's the case, we're never coming back to them. There's nothing that we are looking for. We're ready to do a reduction. And that's the only thing that we can do at that state. We have to reduce. However, states 2 and 4 can be expanded because there are right-hand sides associated with them. So that means that there are transitions out of them. So we're going to go expand state Q2 first. For state 2, it's going to create 5 states, but some of them are going to have the exact same elements in their sets as an existing state. Which means that rather than making a new state, you transition to an existing state. So what makes a state unique is this exact set of elements. So if you make an associated transition here, where you can see that what's associated with it is exactly what already exists, then let's take a look at an example. I'm sure I have an example. As you do this, you eventually reach the fact where there are no unvisited states, your queue is empty of places to expand, and you end up with a DFA that looks like this. Let's see if we can make this make sense. Where are all of these coming from? Take a few minutes, take a look at this, see if you have some questions. I guess I can start by saying something like, the examples of ones that led to existing states was this Q0 on this dot A consumed the A and got us to a position where the marker is to the right of the A. We have that exact same one here. So if we move past the A, then we can also move here. Stare at this for a little bit. What do we notice? Yes. Every possible place we could move that dot gives us some state. How would we navigate this? Imagine I asked you the membership question. Is something in this language? What's an example? What's a string that's in the language? Yeah, the simplest one would just be C. We can go from S to A and A to C, the terminal C. So how do we know that?
You go, transition to Q5 on C.
Yeah. And since we see that, we now can go backwards. We can follow this arrow backwards, saying we found the C. And now we have an A. So we can now visit anything that says we have an A on the stack. So we can now consume this A getting here, which says we can now reduce from here, because this is at the far right-hand side, to get an S. So we follow this backwards and now have an S. Now we can follow this transition that says we have an S on top of the stack, producing this. Now we are done and accept, because we now have, we can consume the S and now transition in our other NPDA to a state that allows us to consume that S, check for the bottom stack character and accept. So you end up having to follow some of the arrows backwards once you end up with something on the far right-hand side. So let's take a look at that process. Yeah.
For like BCA, you would go Q0 to Q4. And then Q4 back, or
So the very first thing we need to do is we need to do a shift. We need to get this B red and on the stack. As we do that, we transition to Q4.
Q4.
So there's nothing reduction wise we can do yet. So we have to shift. So we're going to read this C. So now we're pointed after the C. So from Q4, we go to Q5. Now at the right-hand side, so we can replace that C with an A. So we come back here knowing that we have an A on top of the stack. So our stack has gone from just the bottom of the stack character to then we put on the B. We then put on the C. The C let us replace that solely with an A. So we've done the equivalent now of this, but during this we transitioned back to Q4 because we now had the A on top of the stack. So now that we have the A on top of the stack, we can move past this A.
And then we
So
go to Q7.
Yeah, we moved to Q7 from Q4. So we're able to consume or move past that A. So it says that what we're looking for next here is an A. If it's not an A, this string's not in the language. But luckily, the A is exactly what we have coming next. So this is the equivalent of shifting the A on, which transitions us to Q9. Since it's final, it tells us that we can do a reduction. So we can reduce all of this BAA into an A. But where did this come from to get us to that A? This came from here, here. So as we pop off the A, the C, or sorry, the A, the capital A, and the B, we can look for backwards arrows in that direction. So backwards A here, backwards capital A here, backwards lowercase b here. There's only going to be one of those transitions into that we use to get there. So we'd have to use recursion to do that. Because there are two different B's into this Q4. So which one do we follow backwards? We want to use the one we came from. So going back to Q0, we would see that we now have the A on the stack. So we can take this transition out of that, reading the A to Q3. We're now on the right-hand side of that. So that tells us we can do a reduce, which turns the stack into CS. As we pop that A, we move back to Q0. We have the S on top of the stack, so we can take that transition to Q1, read the S, pop the S, go back to Q0, and we have our empty stack left.
A lot of work.
It is a lot of work, but it allows us to parse in linear time. Which is actually pretty amazing.
Yeah. Great.
Yeah. So let's take a look at the algorithm the last couple minutes. So we started the DFA start state. This is just doing exactly what we already did. Repeatedly apply shift and reduce operations until we have a start symbol on the stack. A shift moves forwards in that DFA. So you just read the next symbol in the string and we follow the transition with that label. As we already did. We push that symbol on the parsing stack. Reduce moves us backwards in the DFA for each symbol on its right-hand side, then moving forwards to the state with the non-terminal on the left-hand side. So we do have to store where we came from. We need a back trace of the history of states that we have visited. Because when we do that reduce, we want to go back via the edges that we came from. So you can only do that if we have an item in a final state with a marker on the far right-hand side of one of its productions. If there are n symbols, we backtrack through n states and transitions that got us to that state. So we're just going to use kind of an undo redo stack. You store the history of where you've been. It really is just an undo stack. You don't need to redo ever, but storing that undo stack and then being able to read from that to figure out what transition to make in reverse. Then we go forwards at that point using the transition of what we just made. The reduction we just made becomes the new shift for the new transition that we read. All right, well, that takes us to the end of class. We're gonna have a full example of this. So we'll come back to the image and we'll actually walk through exactly what happens and exactly what we're storing at the start of class next time. I don't think we're actually going to have a full class's worth of material. We're almost done with this. And again, I mentioned that aside from the concept of an item and a closure and being able to calculate a closure, I'm not going to have you do the entire process of building one of these DFAs or walking through one of these DFAs, just because they end up being so large and gross that I wouldn't really want to throw it on a paper exam. There are too many points where a mistake can be made. And it's too complicated, and we haven't really had homework or a chance really to practice this. So I present this just for your knowledge, but the actual function of calculating a closure is reasonable to ask. So it's on the homework, but I'm actually not even sure it's on the study guide for an exam. I don't really want to ask too much about LR parsing, but it's unfortunate that more grammars are LR than LL. The process is a little bit more challenging, but it's cool when it all works and you realize, wow, I can actually go through and do this in a reasonable amount of time.
Is there LRK parsing? Since there's LR1.
Yep.
Oh, wow.
Yeah, all of that is just with a look ahead of a single character.
That's right.
So we may need to have possible transitions that consume multiple characters to be able to remove that ambiguity. So yeah, it gets even worse. Yeah. That's what we have time for. I'll be headed back to my office for some office hours if anyone has questions about any of the content. And there's quite a bit of it. So hopefully you come up with questions and I can be useful to you.